doing an FIP program uh, in MMTTC Center at Pandit Ravishankar Shukla University, Raipur. So first of all, my name is Dr. Hardeepbhai Jorubhai Khachar, and I am affiliated to Government Science College, Bhilad. And the university that we are affiliated to is Veer Narmad South Gujarat University, Surat. So basically, this content requires a basic knowledge of mathematics. So students must be aware of little bit of Fourier series. So I guess undergraduate and postgraduate students who are aware of Fourier series can learn this concept easily. So this is basically my research level topic, and I studied this series, and I only included the basic and starting points of this content. So let's begin. The classical Fourier series, as we all know, is generalized by various orthogonal Fourier series like Legendre, Vos, Chebyshev, Haar, and many more. So we have different types of Fourier series with respect to different orthogonal system, and we use this for various applications. Like if you want to approximate different types of functions, we want convergence properties to be better, or we want applications in mathematics, engineering, and physics, and we need some discrete data, and we use Walsh series as well. So there are various applications of Fourier series, not only in classical Fourier sense, but also with respect to different orthogonal system. So the choice of orthogonal Fourier series depends on specific problems and applications. So here we are going to talk about rational Fourier series. So there are some drawbacks of classical Fourier series. Like if we want to deal with functions with discontinuities or which are non-periodic in nature, then the classical Fourier series is not very efficient, and rational Fourier series is more suitable, as already discussed by Esner and Pep and Chen and others in their respective papers. So let's begin with what is rational orthogonal system. In 1920s, the rational orthogonal system were independently defined by Malmquist and Takenaka, and the system is called Malmquist-Takenaka system or rational orthogonal system. The rational orthogonal system is as defined in this equation 1. Now this looks little bit complicated, but yeah, this is the system. So if we take alpha is equal to 0 everywhere, here, and everywhere, alpha is 0, then we get our classical exponential system, that is e raised to I and xk. So basically, this is in a way generalization of classical exponential system. Here again, alpha n's are a complex sequence, alpha k is in open unit disk D. And it was observed that this system is complete in L2 if and only if this series 1 minus mod alpha k is divergent, and it was proved by Esner. And the simplest way to satisfy this condition is to assume that so basically is to assume that supremum of mod alpha k is less than 1. Okay, so in the sequel, we'll assume the condition 2 holds, that is the supremum is less than 1. And again, z star is z minus 0, t is close 0, open 2 pi, and t bar raised to n is t bar cross t bar cross t bar n times. And phi n is a real sequence such that phi of 1 is greater than equal to 2, and phi n is increasingly tending to infinity as n tends to infinity. This will assume for rest of our discussion. So in 1956, the concept of rational Fourier series with orthogonal system as rational orthogonal system was introduced by Servatian. So he gave different results based on this. So if we take a 2 pi periodic integrable function, then rational Fourier series of f is defined as in this equation 3, where f at n is nth rational Fourier coefficient of f given by equation 4. Again, if we take alpha k equal to 0, then this system reduces to exponential system. Therefore, this series would reduce to Fourier series, and the coefficient would be Fourier coefficient. So the pursuit of elegance and generality by mathematicians in addressing specific problems has resulted in various extensions of concept of bounded variation. So we are getting various novel generalized bounded variation classes. So some of the authors who defined bounded variation as generalizations are Jordan. Jordan was the first one to define bounded variation. Later on, they were generalized by Wiener, Waterman, Kita, Yoneda, Ekobets, and many more. So in 2013, the following property of rational Fourier coefficient was obtained, that if f is integrable, then modulus of f at n is less than equal to as defined in inequality phi. So this inequality is basically satisfied, where again omega 1 f delta is supremum of integration 0 to 2 pi mod of f of x plus h minus fx dx, where 0 less than s less than equal to delta. Now if we see here that this is analogous to Riemann-Lebesgue lemma for Fourier series. So if we take n tends to infinity, then this would obviously go to 0. as this would go to 0. And similarly here, if you take n tends to infinity, this term would also go to 0. So this to both the terms would tends to 0 and f at n would tends to 0. So that is basically our Riemann-Lebesgue lemma. So this can be considered as rational Riemann-Lebesgue lemma. So the generalized bounded variation due to Vyas as given as below. If f is complex valued measurable function defined on an interval I, AB, and lambda k is a non-decreasing sequence of positive numbers such that series 1 upon lambda k diverges, and for 1 less than equal to p less than equal to infinity, 1 less than equal to pn increasingly tending to p as n tends to infinity, then f is said to be in this lambda bounded variation if this variation is finite. Now this is little bit complicated, but basically here the variation is defined as summation mod of f of im raised to pn by lambda and whole raised to 1 by pn. And here im are finite collections of non-available subintervals of I, and f of im is defined as f of bm minus f of am, and delta im is of infimum of mod of am minus pm. So this is basically a generalized variation, and kind of it is more general than the previous variations that we have discussed. And this is the basic definition for generalized bounded variation. So if f is in this lambda bounded variation, then f is clearly bounded function on I. Now, if we take lambda equal to 1, then again, as I said, that it reduces to previous variations like given by Jacobi. And if we again take phi n is equal to 2 raised to n, here phi n is here. So if we take phi n is equal to 2 raised to n, then we get the variation due to Kita and Yoneda. So I, with my guide, Professor RGV, we derived this result. If f is of lambda bounded variation and n is in z star, and 1 less than equal to p less than equal to infinity, then f at n is of order this. So the decay rate of Fourier rational Fourier coefficient is this one, 1 upon summation 1 upon lambda j whole raised to 1 upon p of tau of mod n plus 1 upon mod n. Here tau n is defined as this one, as given in equation 9. So this we have derived. So next, Jacobi also defined the variation as below. Let f be a 2 pi periodic measurable function and p and b increasing sequence such that these conditions as previously mentioned are satisfied. Then f is said to be lambda variation if this variation is finite. Here instead of summation we are using integration. So this variation was defined by Jacobi. So if any function is in this variation, then that function is obviously essentially bounded function, and it was already proved by Jacobi in the same paper. So again, I with my guide have proved this result, that if f is of b lambda variation, that f at n is of order as given in equation 11, where tau n is defined as in equation 12. Okay, so this is also analogous to Fourier coefficient results. Similar Fourier coefficient results are obtained. So now the question is, like, all the results would be same as Fourier coefficient, or would it be differ? So next, if we see that there are differences in properties between rational and classical Fourier series. So for example, we are defining convolution as below. If f and g are two integrable functions on t bar, then convolution product is defined as in equation 13. So in Fourier coefficient, it is well known that convolution of f and g, Fourier coefficient of convolution of f and g is equal to Fourier coefficient of f into Fourier coefficient of g. But this result fails for rational Fourier coefficient. Okay, so here with this simple fx equal to gx equal to sin x and n equal to 1 and alpha 1 equal to half, we get that f at 1, g at 1 are equal, but f star g at 1 differs from f at 1 and g at 1. So the result, this result of classical Fourier series does not hold for rational Fourier series. Now, if we see that why the rational Fourier series are important, already we have Fourier series and it have many applications. So first very important point is that with appropriate selection of parameters, but by that I mean alphas that we have taken, rational Fourier series exhibits very faster convergence and better accuracy than classical Fourier series. It was proved by Plonka, Potocka, and Quine and others. So it has already been proven that rational Fourier series for certain parameters exhibits faster behavior. And besides the theoretical applications that we have already seen, there are various applications in fields such as control theory, system identification, signal processing, denoising, and many more. The one slight drawback that we can see is that it is computationally complex and intensive to calculate rational Fourier coefficient. It has the orthogonal system is little bit complication, but otherwise it has very good good applications in the field. So later on, we have also proved result in rate of convergence of Fourier series. We have also derived certain results on order of other generalized bounded variations, and we have also defined results on rational trigonometric series based on this concept of rational Fourier series. So this was part of my PhD thesis as well, and I was quite excited to share this knowledge with all the participants in this FIP and others who are listening to it. So that's it. And these are the references where I have taken the content. So these are all the papers that I have studied during my PhD. Thank you. That's all from my side. And if any query or any discussions related to this topic, you can contact me by my mail. I think I have displayed it in on the first page. Yeah, here it is. So it's Hardeep1996k@gmail.com. Thank you.